All right, we're going to begin lesson 7.1 today. It's on graphing systems of equations. Really, today is going to be more of an explanation and talk about solutions to systems of equations and how those operate. Tomorrow, we're going to get more into the graphing concept. All right, so an example of this, where could you use this is generally the question asked. What good is this? I know most of you don't have to deal with this, but decisions have to be made sometimes and as adults, and when you deal with cell phone companies, it's no different. So in this situation, we have two cell phone companies. One charges you $34 for five, in addition to 5 cents per minute that you talk. Company B charges $40 uh, as a general fee, and then $4 per minute for talk. And the idea here is which one is better, which is a better company to go with. And let's just say that they pretty much give you the same product, same service, and so forth. All right. Well, this is an example of a system of equations, and even a good example of how graphically it can really help you to use a system of equations. Okay. So let's take company A and write its equation. So the C stands for total cost. So the total cost that you pay for company A's service is going to be 0.05, 5 cents times the number of minutes you talk plus $34. It's a monthly fee. Okay, company B is its total cost is 4 cents a minute plus $40 as an initial fee. All right, so that's writing it as a system. This is now considered a system because we've got two equations that involve the same two variables. Even more of a benefit, now that we put it in this format, is to look at it graphically. So if we graph these two, you can see the red line is equation A and the blue line is equation B. Okay. Now, as you analyze this, and I said, what was the better company for you to use? I don't think you can just say one or the other. I think you have to look at how you're going to use it and some other factors. For example, if you use, let's say, over 1,100 minutes a month on your plan, so you're on the phone for over 1,100 minutes. So go down here minutes to 1,100. You're going to notice you're going to hit the B line first, and then you hit the red. So B at 1,100 minutes is a little over $80, maybe $82, $83. And it looks like, the red one, company A, is almost up to $90. So there's a little savings there if you go with plan B when you use more than, the 1,100 minutes. Now, if you're going to go, let's say you typically use less than 450 minutes or underneath that. Now, when you go to 450 and go up, you hit the red line first. So that means it's a little cheaper than the other company, which is the blue line B, which is above that. So if you're going to use under 450 minutes, you're probably better off going company A. The C says here, well, how many minutes of talk time do you get the same monthly statement? Or in other words, when is the cost the same? So if you look up here at 600 minutes, it looks like at 600 minutes, regardless of the company you choose, you're going to pay the same amount. This is actually the solution to the system. Okay, a solution to a system is the point that they share in common. It's the one ordered pair that make them both true. All right. So to answer the question, which company would you go with, A or B? I think it depends. If you're going to use less than 600 minutes a month, I'd go with A. If you're going to use more than 600 a month, I go with B. So it helps to analyze data like this to look at a situation and show you how graphing systems of equations actually is beneficial. Okay, now let's get into a little bit of the basics here. Solutions for a system of equations. First of all, a system of equations, like I said, is a set of two or more equations that use the same variables. Like in my example, cost was equal to a dollar amount times the number of minutes plus a dollar amount. That both of those two equations use the same two variables, cost and minutes. So that was a system. It can be x's and y's, it can be c's and m's, as long as both equations use those variables. Okay, a solution to the system is an ordered pair that's a solution to both equations in the system. In other words, an ordered pair and xy value, typically were xy's, that when you substitute it into either equation, it makes them both true. So you're looking for the ordered pair that makes both of the equations true in the system. Now, what can happen? Well, we could get one solution. All right, there is a scenario where you have a system of equations and you get one solution. That means there's only one ordered pair that can make each equation true at the same time. Graphically, that's when two lines intersect. Their point of intersection is that one point, is that one ordered pair that makes them both true. Now, the label we give that is it's called a consistent independent system. I think of independent means you're out on your own. There's only one of you, right? So there's one answer here. And we're going to use these labels in homework tonight. All right. You could get one solution, you could get no solutions. Okay. And a system of equation that has no solution means there's no ordered pair that can make both equations true. Now, when is that? When do you see that? Well, you see it graphically when the lines are parallel. When lines are parallel, they are never going to intersect. And the only time we can get ordered pairs that make both equations true is when there's an intersection. All right. Now, when there's no solution, in other words, the lines are parallel graphically, that's called an inconsistent system. You'll need to know that. And then the third possible scenario here is that you get an infinite group of solutions. In other words, there's an unlimited number of ordered pairs that make both equations true. This scenario is when you graphically have the same line. They may be given to you differently, but when you go to graph it, it's the same slope, it's the same y-intercept, it's the same line. So every ordered pair that makes one true makes the other one true because they're the same. Now, we call this a consistent dependent system. Okay, consistent dependent system. Okay, let's look at some of the questions you're going to see tonight. First type of question, and we've had this before. We did it with inequalities. We did it with equations. Now we're doing it with a system. And the question here is, are any of the ordered pairs listed here solutions to the system? All right. If there's a solution to the system, that means they are an ordered pair that make each one of these true. And if the ordered pair makes the equation true, that means it's on the line. So we're looking for an ordered pair that's on both of these lines. In other words, it makes them both true. So to test this, rather than graph it and look at all these, we would rather just use some algebra here. I'm going to take both of the equations from my system, and I'm going to substitute in the values of x, y to see if it makes them true. So I'm going to do one at a time. So I'm going to put -4 in place of y. I'm going to put 2 in place of x. Okay, I'm going to get this line of work, and when I do my calculations, I get -4 equals -4. That's a true answer. So that means 2 -4 is on the line. Now my second equation, okay, I'm going to plug in the same thing. I'm going to put 2 in place of x, -4 in place of y. I'm going to get 6 plus 8 is 7, 14 equals 7. That's false. Okay, so if your ordered pair doesn't make both of these true, then it ain't the solution. Okay, it's not the solution. It's got to make them both true. All right, let's move on to the next order pair. Y equals 2x minus 8. So start with x is 9, y is 10. So y is 10, x is 9. I get 10 equals 10. That's true. So it is on the first line. Go to check the second one. 3 times 9, 2 times minus 2 times 10, 27 minus 20, 7. That's true. So this ordered pair 9, 10 is on both of these lines. That means they share this point, they intersect. That's a solution. Okay. Now we got to check them all because there could be multiples if these two wind up being the exact same line. Go to the next example. X is -6, y is 0. Plug it in. Simplify. 0 equals -20. False. Now, if that first one's false, I'm not checking the second one because it's got to make them both true in order for it to be an answer. Right away, this one's eliminated. That's not a solution. Okay, my last one, -1, -5. So put -5 in place of y, -1 in place of x. I'm going to get -5 equals -10. That is not true. So this one is also not going to be a solution. So the work you do tonight will be this kind of stuff. You know, the work you have to show for tomorrow is that kind of stuff. All right. Okay, moving into some more questions. There's two types that look like this. The first one is, let's just tell us the outcome. What's going to happen here? For each system, choose the best description of its solution. If the system has exactly one, then name it. Give it solution. Okay, so here's line one. You see L1 right here. Okay, you know how to graph these. So we cross the y-axis at 1. It's got a slope of -2. That's up to the left one, up to the left one. There's line 1. Here's line 2. It's got a slope of -1 and 0 for the y-intercept. So I start here at 0, up 1, left 1, up 1, left 1, draw line 2. These two clearly intersect right here. So there is one solution, and that one solution is at 1, -1. Okay, go to our next one. Okay, as soon as you see the graph, you should see that these two lines are parallel. What also confirms they're parallel? Their slopes. Go up here and look at their slopes. Both have a slope of 2/3, y-intercept of 0, y-intercept of 4. These two lines are never going to cross. There is no solution to this system. Lines are parallel. Okay. This one, y equals x. L1 is this graph. Opposite of x plus y equals 0 is also this graph. If you were to add x to both sides, you would have y equals x, y equals x. That's the same line. If it's the same line, you got an infinite number of solutions. Okay. Now the next question has you do the same thing you just did, plus give a description of the type of system. Okay. So this first one, y equals 4, horizontal line going through the y-axis at 4. Y equals -2, horizontal line going through the y-axis at -2. Horizontal lines are parallel to one another. Therefore, there is no solution, which makes it an inconsistent system. No solution, inconsistent. Okay, next example. Here are my two equations. When you graph the first one, you get this line. To graph the second one, guys, you'd have to solve this for y. And what you would do as you solved it for y is get this answer again. So when you graphed it, you'd be right on top of it. All right, that means we got a consistent dependent system, and there's an infinite number of solutions. And then our final example here. Here's my first line. Here's my second. Okay, we graph them both here. We can see they clearly intersect at one point. So that means I got a consistent independent system. There's one unique solution, and that one solution is right here at -3, -2. Okay. So that's the beginning part of graphing systems of equations, kind of the fundamentals, the makeup of it. Tomorrow, we're going to get into actually doing more graphing and finding solutions. But today is kind of just working through the base concepts. All right. All right. I'll let you have at it.